here we go. So let's do a quick treatment of number 6, and then we can start to go into new material which relates to problems 7 through 12. Now in number 6, the problem states that a pitcher claims he can throw a .145 kilogram baseball with as much momentum as a 28.4 gram bullet, moving with a speed of 224 meters per second, which is about 500 miles an hour. What must the baseball's speed be in miles per hour if the pitcher's claim is valid? So in order to solve this particular problem, I am going to make use of the fact that I have multiple colors, because basically we have 2 objects in this problem. What are they?
The bullet and the baseball?
We have a bullet and a baseball. So we are going to do the bullet we'll put in blue and the baseball in red. Now, both of these objects, all we are talking about is momentum. That's all. So what pieces of information do we have about either one of these that they give us? Anybody? Okay, Alexis? Okay, they give us the mass, and what is it? 28.4 grams. Now, people can address this in different orders, but I'll go ahead and go. Is there anything you want to tell me to do about this? 2? Right. So I think I was doing that in orange last time. So I'll say we do have to get this converted to kilograms, but I'll leave that up to you. All right? What else do we have? Okay, Michael?
The mass of the baseball is 0.145 kilograms.
Okay, so they give us, it would be red M, and this is already kilograms, so we're good to go. No need to convert there. Okay, what else? If we don't identify anything else, we are kind of stuck at the moment. Okay, Stella?
The bullet's velocity of 224 meters per second.
224 meters per second. Do we have to do any converting here?
No.
No, because remember, MKS is meters, kilograms, seconds. So we got meters and seconds, so we're good there. We need to take this gram to kilograms, and then we could start to crunch numbers. Okay? Now, what is it that some people might not get this right at the beginning, but I'll go ahead and address this. What is it that we're supposed to calculate or figure out?
The momentum of both of them?
We do have to figure out the momentum of both of them, but what are we eventually trying to find?
To see which one went faster.
No.
We'll have to find what velocity the baseball will have to be for the pitcher's claim to be true.
Yeah. We need to find this. But we don't know what that is. But what is the one thing that they say, because Michaela brought up momentum. What did they say about the momentum of the 2 objects?
They should be the same.
They say the claim is that they have the same amount of momentum. What is our, I'm going to put this in black. What is our equation for momentum?
P equals M times V.
That's our big equation. Which one of these could we actually calculate the momentum for?
The bullet.
We can actually go ahead and find this. Now, remember, I got this color coded, so this is in blue. So I could figure out what this number is here. What am I going to do with this blue P?
Plug it into the equation for the baseball.
Right. And since I'm doing colors, we could call it red Sounds bad to say red P, but that's what it is. So what we can do is we could say, once we calculate this, that is going to go in for that, because it's supposed to be the same. And since we have the mass of the baseball, all we would have to do is divide across by the mass to get this velocity. What's the additional thing we're going to have to do with the V?
We'll change V to miles per hour.
Right. When we solve for V, it will come out in meters per second to begin with, but the problem is asking us to express the answer in miles per hour. So we'll have to do, so I'm going to do this. Answer in meters per second. And so I'll highlight in orange here. Convert to miles per hour, and then you would be done. Okay, so this is problem number 6, kind of all mapped out, not done for you, but kind of set up with instructions. Now you guys can already see what the answer is. So if you're familiar with baseball, is this a legitimate claim? Yeah, there are regularly pitchers who can throw over 100 miles an hour. So I don't know what that means for a batter who gets hit with a ball, because it's kind of like saying if you get hit with a 100-mile-an-hour fastball, fortunately it's a big thing, so it doesn't have the penetrating power that a bullet does, but from a momentum perspective, they're comparable. Yeah.
I mean, that's actually enough force to break somebody's skull. That actually happened to a person. So
Yeah.
it's actually a case.
Okay. Anybody need to get a quick picture? Although you can always watch the video and see it all mapped out again. We're good? Okay, so I'm going to erase this. And now we're going to talk about our new topic today. And it's actually 2 things that we're going to bring together. The idea that something has momentum in and of itself doesn't mean much. You know, for example, you could talk about a bullet. You have a bullet going 500 miles an hour. It has momentum. But in order for that, I want to say, in order for it to do something or to talk about it, it needs to have an interaction with something. If you say, well, I have momentum as I'm moving down the street, if you never actually bump into anything or talk about, well, how did you get that momentum? Because you were probably not always moving to begin with. It's pretty boring. When an object is moving and we talk about it having momentum and that's as far as we go, its momentum never gets bigger, its momentum never gets smaller. It really is kind of boring. So when things get interesting is when we talk about a change in momentum. Now, if I was to write the symbol for the change in momentum, what would that look like? We're going back to basic science things here. Levi?
Delta P.
It would be delta P. Okay? Now, what if I asked you, how do we expand this so that we actually have some math over here? Anybody know what I'm referring to?
The first and final one.
Okay, and what do? You have a first, we'll call it initial,
Initially.
and you have a final, and what math are you doing with them?
Subtracting.
subtracting them. So it's the final one minus the initial one. Okay? Now, when it comes to measuring momentum, we don't have like a device that directly measures momentum. I think you'd call that thing like a momentumometer. We don't have them. What we have are devices that can measure the mass of an object and its velocity, and then we figure out what the momentum is. So if we were to break this down mathematically, what could we break this down to that we've talked about already? What equation? Matthew? What? M times V. Now, which one of these do you think is more appropriate to have the F on? If we're going to change the momentum of an object, will the M be changing? Probably not. That would be a weird, like you're losing mass or you're gaining mass. We're not going to go into situations where that's happening. So when we talk about something like gaining or losing momentum, the thing that's going to get the final or the initial subscript is going to be the V. So that means that our initial momentum will be the same exact math equation, except the V will be the initial velocity. Now, we could do a little bit more math with this, but I don't think it's really going to be all that helpful for us. So I'm going to stop with this discussion here. And I'm going to go to another place that, I don't know, some people going, why the hell are we going there? Hopefully you'll see at the end here. See if you've been paying attention. Where's my favorite place to go when I want to talk physics stuff and motion, things moving?
Football.
Momentum, football is a good one, but I have a general place.
Safeway.
The grocery store. Okay? And when it comes to objects moving around, what's my object?
Shopping cart.
The shopping cart. Okay? So I go to Safeway. Shopping cart. Is it moving? No. But then I put my hands on it and I do my thing. Now it's moving. What does it have now that we've been talking about that it didn't have before?
Momentum.
It has momentum. Where did that momentum come from? Well, it has momentum because it has a velocity that it didn't have before. Correct. Where did all that come from?
The force of you pushing it.
It was me interacting with the cart, and in particular that idea of force, because they say you pushed on it. And when we talk about a push, that is a force. So we are going to talk about we're going to do this because I like units too. So let's I'm really going to be putting a bunch of colors up here. What is our unit for momentum that we talked about it when we first introduced the topic to you?
P.
That's the variable. What were the MKS units that go with momentum? It was kg m over s. Okay? So we just finished talking about this idea that the shopping cart didn't have momentum, but then once I interacted and provided a force, it ended up with momentum. So I'm going to see if we're going to show you how sometimes you can play with units to figure out equations. What unit do we measure force in? The simplistic answer is newtons. That was the nickname. Can you give me the MKS unit that we had for newtons? Matthew?
Is it kilograms times meters over seconds squared?
Correct. Kilogram times meters over second squared. And that came from our Newton's second law. Force equals mass times acceleration. Damn, these are pretty damn close, aren't they? What could I do with this if I wanted it to become that?
You square root it.
Well, if I square rooted it, if you're focusing on this, saying if I square rooted this, then that would give me that. Close, but if I did a square root thing, I'd have to do the whole thing. So that would mess this up. Can somebody think of something else we could do to take some kind of math we could do with this to end up having it become that? Okay, Matthew.
You multiply by seconds.
If we multiplied this by seconds, what happens with our seconds and our seconds squared? This would cancel just one of these. Okay? So here's where I'm going to see if you kind of can connect the pieces. This goes with that unit, which went with this. What variable goes with this? Come on, you can do it. If you're just talking about seconds, what is that?
Time.
It's time. What variable do we use for time? That's the unit. What's the variable that we use when we have our equations when we're using time?
Lowercase t.
Lowercase t. And what are we doing with these two things here, mathematically? Multiplying them. So, when we multiply these two things together, we end up getting this exact unit, which is the same thing as momentum. So if we take a force times an amount of time that the force acts on an object, that has a special name. Well, actually, let me do it on the other side. We're going to call that thing a capital I. Okay? And if you're going, what the hell? I will agree. You have probably never heard of this capital I thing before. It is called impulse. Now, here is the part that's a little bit different when we go for how do we measure impulse? We usually do not measure impulse in kilogram meters per second. We keep it based on this equation. And we already said that force, we usually talk about being represented as newtons. And T is measured in seconds. So when we talk about impulse, we don't really talk about it in terms of kilogram meters per second. We talk about it in terms of what we would call a Newton second. Now, if you stopped anybody on the street and you asked them, do you know what Newton seconds are? And somebody said, oh yeah, that's impulse. You're probably not going to get very many people who can actually answer that. And if you do, you know that that is somebody who took a physics class and paid attention in that unit, because this is not something that is usually thrown around as commonly as things like meters per second or even meters per second squared. But the reason it comes up in this unit is that impulse is tied to a change in momentum. So going back to the shopping cart, I said that initially, when I walk up to the shopping cart, I got it. Anybody have access to a shopping cart like that a store would let me have one? If anybody ever gets their hands on a shopping cart, you know, and they're like, you know, my teacher really likes to talk about a shopping cart. You know, do we got like an old one that we could give them that you'd want to give away? It's like, I'll take it. Then I got this visual thing I can like push around here, you know, while I'm, because I know you all can visualize like pushing a shopping cart, but for some reason it's like deeper when you actually.
Just take one from
Yeah.
Safeway.
I'm just not gonna take. I need it to be like donated or given. So if you are aware of anything like that, let me know. There are times when I see them on the side of the road that I'm like, oh, dude, I should just grab that one. But I haven't seen one recently. Did you have a comment, Andrew?
Safeway route.
What?
The Safeway route.
Oh, okay. Although those are real fancy though now. I like, see, look, I want a grocery cart and now I'm getting picky. I like the mini ones. You know how they have the bigger and the smaller version? I kind of like the smaller version.
Trader Joe's ones, kind of.
What?
Like the Trader Joe's ones. They're not like huge, but they're smaller.
Yeah.
Yeah.
Fit little more compact. So if you guys are aware of any of that, let me know. I'll go pick up. So when we talked about the shopping cart, we said, all right, when I first come up to the shopping cart, no momentum, it's just sitting there. And then after I've interacted with it, wow, now it's moving. That means it has undergone a change in momentum, and now it has momentum that it didn't have before. But we pointed out earlier, Andrew brought up when I said, well, where'd it come from? You mentioned, well, there's a force that came from you because you pushed on the cart. What's the other thing that we would have to measure about my push on the cart in order to calculate this for what I did on the cart? Because how hard I pushed on the cart would be this. But what else would I need to know in order to figure out how much impulse I put on into the cart?
How long you did it?
How long I pushed. Now the truth is, if you're talking about an empty shopping cart, realistically speaking, do you have to interact with it that long in order to get it going? Not really. So, but anybody ever push start a car? Okay. Or maybe not even push start, but the car died and you needed to push it, you know, to get it off the road. Definitely have this, but your T is probably a lot bigger than me pushing on the shopping cart because the car or the vehicle is that much heavier, so you have to really push for a significant number of seconds to give that thing the momentum to get it rolling. So the concept that we're going to link here is going to be this impulse is connected to this here because when I made the shopping cart go from rest to actual motion, the reason that happened is because I provided an impulse that became the momentum of the cart. Okay? Now, I'm going to write this thing in underneath here. All right? And this is kind of the big kind of coming together of all of this. There is a theorem. This is the first time we've really seen this happen this year, but we will see it happen at least one more time later on. There is a thing that is called the impulse momentum theorem. And I'm going to give you two versions of this. One is the summary version, which is kind of like, tell me the story about this. The other one's going to be the mathematical version of it. Here's the quick summary version. Capital I equals delta P. So this says the impulse that acts on an object is going to cause or result in a change in momentum of that object. So in my example, which one of these is me? Impulse or a change in momentum?
Impulse.
I am the impulse. What's the delta P?
Change movement.
Of what object? The cart. So when you think of the impulse momentum theorem, I'm going to put two words up here. Let's see. No, what did I call? Oh, yeah. I think of this as a thing that I refer to as an agent and then an object. The agent is responsible for the impulse. The object is the thing that actually undergoes a change in momentum. Now, I tried to make this really simplistic with the shopping cart example. We just did a baseball example. How could you do a baseball and pitcher? How could you relate this to that? Which is which? Baseball and pitcher. Come on. Somebody can do this. Okay, Michael.
The baseball's the object and the pitcher is the agent.
Correct. So the idea is that with the baseball and the pitcher provides an impulse just by literally applying a force for a certain amount of time while they go through the windup that ends up becoming, or you could, in a way, you could say it gets transferred to the object, which in this case is the baseball, and the baseball undergoes the change in momentum because it wasn't moving before it left the pitcher's hand, and by the time all of that impulse, because the impulse doesn't happen at an instant with the pitcher. They go through the elaborate windup and everything, and as they are moving that ball all around, that is all impulse, and then they let go, and the idea is that the baseball was not moving before the windup, now it is. So it has undergone a change in momentum. Okay? What about, let me make sure we got enough time here. Oh yeah, we're good. A car. Let's do this. A car starting like you want to pick up speed. What's our impulse object or impulse change in momentum or agent object relationship with that? Come on. Okay, I'm just going to ask somebody. Okay, I'll go for it, Julian.
Would the agent be the person driving an object in the car?
Okay, because now, we're going to get a little more detailed here because we're talking about like you were stopped and then you want to start going. So what does the person do to make all that happen?
Pressing on the gas pedal.
They press on the gas, and because of that, what happens?
The car goes forward.
Right, because there is this complex thing where that feeds gas into the engine and it combusts, and that generates a force that then acts on the car that allows the car to pick up speed. So the idea is that the person / engine, because that's where the interaction is, produces an impulse that acts on the car, and in this case it's a positive change in momentum because the car picks up speed. Anybody want to go with what happens when you approach the stop sign?
Slow down.
What's the thing that goes on here? You slow down, and let's say you're going to be a good driver, which means what do?
You stop.
You come to a complete stop, right? All of you are good. I'm not. I'm horrible, but I know you're supposed to. So you're going to come to a complete stop. Where's the agent concept there? It kind of parallels what Julian threw out for the picking up speed. Where's the impulse coming from for this? Oh, there's a stop sign. I got to stop. Bryce? The brakes. And so you could still tie it back to the person, because the person will step on the brake, and that will generate a force because of how the brake system works that will act for a certain amount of time, and that will end up causing a change in momentum. But how will that change in momentum be different from the change in momentum for the person in the car when the person hits the gas? Sign-wise. It'll be negative because the person will be losing speed because they're going to slow down for rest. Okay? So this impulse momentum thing, it is all around you. Anytime you shove something to place something in motion, this is at play. Oh, here's another one. Anybody play tennis? No tennis people? Oh, man. Okay, you guys know tennis though, right? Okay. The serve. Where's the agent? Where's the object? Anybody? Okay, Michael.
The agent is the tennis player and the object's the tennis ball.
Correct. And what is the thing that, you know how we said, like with car, when we were talking about the car example, we said it's the person because the person either steps on the gas or they step on the brake to cause the impulse. What's the thing that connects the person to the ball? The racket. So the idea is that the person is the agent, and through the use of the racket, which is the agent, they provide a force that acts for not a long time, but for a short period of time, and that acts on the ball, and that takes the ball from just kind of hanging up there to giving it whatever speed it has coming out of the serve. Okay? And we're going to talk about strategies in sports a little bit later when it comes to this impulse momentum theorem. Now I need to add one other thing with this, because this is the conceptual treatment of the impulse momentum theorem. But we have a couple mathematical formulas here, and this is where we're going to substitute those in. What's our math formula for impulse that we have up here? I'm not going to point to it. It's on the whiteboard. What does I equal?
F times T.
F times T. What does our delta P equal? This one's a little more elaborate. Okay.
Your final momentum versus your initial momentum?
Yeah. And remember, usually you're not going to be given this as a value, but what you'll have to do is you'll have to use this version of it because they'll give you information about the mass of the object and its velocities. So on this side, we're going to have that one there is the important, and I'll go ahead and box that in red. This is the, I'll call it the important math presentation of this thing that we call the impulse momentum theorem. Now, I want to highlight one last thing. And then what we'll probably say is, we'll give you a day off and say tomorrow we'll take a little bit of time to go through some of the sample problems, and I'll say, if you want to try using this with some problems, I'll let you kind of go on your own overnight. But tomorrow we'll do a couple setups and then give you time to work on it in class after the unit conversion quiz. There is one big reason why we can set these two things equal to each other. Because some people will say, wait a minute, the unit for impulse is this Newton second thing. The unit for momentum is kilogram meter per second. But what did we discover about those two units over here? This is the big deal about this.
That we're still using like the same concepts from the original of the year, like with velocity changes, and like we're incorporating all of this into here.
Not quite.
Impulse is equal to change in momentum.
Impulse is equal to change in momentum, but there's one big reason, and usually you don't have to worry about this, like to get a problem correct or not, but there's only one reason we can actually say this. Levi?
Is that because the bottom is both seconds?
Correct. This thing here, Newton seconds, that's technically this, but when we multiply it by seconds, we get this. What is this the unit for?
Seconds. Time.
The whole thing.
Momentum.
It's the same unit for momentum. So when you take Newton seconds and you actually play with those units, you actually end up with the exact same unit as momentum. That's the only reason that you can set these two things equal to each other. Even though Newton seconds doesn't look like this, it actually is. But we don't talk about, because the equation for impulse is based on a force times the time, we usually use Newton seconds to talk about impulse, but the thing you have to remember is from a dimensional analysis perspective, it is the same thing as momentum, and that's why we can set these two things equal to each other. Okay. Anybody have any questions? Okay, so for those go-getters who are looking at this going, ooh, can I try some? Problems 7 through 12 are all about this. And so if you want to try any of those between today and tomorrow, you are welcome to do that. But tomorrow we will do a unit conversion quiz early, and then we will go through some of these and set them up for you. I will point out one last detail that will come up, not all the time, but you have to pay attention to. And we kind of talked about this with when we mentioned the car. What would be a difference between the type of impulse you get between pressing on the gas versus pressing on the brake with a car? If you want to express that difference mathematically. Anybody know what I'm fishing for?
Negative versus positive.
Correct. Which one do you think would be the positive impulse?
Gas.
Stepping on the gas. And when you step on the brake, you would have a negative impulse. Which variable in the impulse equation here, which one brings the positive or negative into play? F or T? The F. Because a force can act, it's a, what do we call the things that have direction? The word? No.
Vector.
A vector. Force is a vector, as is velocity. And so velocities and forces can be positive or negative, so sometimes you got to pay attention to those details in the description of the problem. So we'll try and highlight that for you when the time comes. Okay, now I am really done. So I'm signing off, people in video land.